The next example that I'm going to show you is a model that uses the log normal likelihood. Now, if you remember, I showed you a model earlier where we were just modeling button pressing times using a very simple linear model. And so we are going to revisit that data now. This is the spacebar data set. And this time, what we're going to do is we're going to model the effect of trial ID, which is a discrete number starting with 1, 2, 3, 4, and so on, which represents the row ID in the data frame that we have. So if a subject presses the button 200 times, row ID will go from 1 to 200, right? So why are we looking at trial ID as a predictor for button pressing times? Because we know from research in psychology that what happens to subjects, to participants when they're doing an experiment is either they're going to start speeding up because they get more used to the task or impatient or something, or they start to get fatigued and they start slowing down. So you could get a positive effect of trial ID on button pressing time or negative effect. We can't be really sure, right? So that's why we are interested in trying to understand whether trial ID will affect button pressing time. So again, as before, I'm going to first center trial ID so that the value 0, in the center trial ID, the value 0 means the average trial ID. If there were 200 elements in the rows in the data frame, then 100 would be the midpoint of that experiment. So that would be recoded as 0, and all IDs lower than 100 would be negative, and all IDs greater than 100 would be positive. That's what centering does, right? All right, so here's my model again. There's a simple model, just like the normal likelihood I showed you earlier, except for this important change. Now I'm assuming a log normal likelihood. Why am I assuming a log normal likelihood? Well, the reason is that the reading time cannot be negative, right? It has to be positive. You can't have negative button pressing time, right? And so you want to have a distribution that is skewed somewhat to the right, that has a slight skew to the right. And the log normal has exactly that property. So that's why I switched from the normal likelihood to the log normal likelihood. And of course, we have much more to say on log normal likelihoods in the textbook, but right now I'm just getting to the point right away, right? So what changes now is that instead of, I have the same parameters as before, okay? So I've got an intercept parameter, slope parameter, and sigma parameter, right? So this is pretty similar to the model I just fit earlier, looking at pupil size and attentional load. The difference now is that I'm assuming a log normal likelihood, and that implies something very important. What it implies is that I'm now going to have to define priors on the alpha, beta, and sigma parameters on the log scale. I cannot now operate on the millisecond scale and think about the average button pressing time on the millisecond scale anymore, because I'm working on the log in the log normal distribution, right? So what I'm doing here is that I'm defining a prior for alpha, for the intercept, using a normal with mean 6 and standard deviation 1.5. This is on the log scale, right? So what would this be on the millisecond scale? It would be the exponent of 6. That would be the location parameter on this in this distribution, right? On the millisecond scale. So that's why it's very important to now switch gears and to start thinking about the parameters on the log scale, right? So that's why I'm defining everything now on the log scale, because we are working with the log normal, okay? So for the alpha, I've defined this parameter. Of course, one question that you should have is, how did I decide what this prior is going to look like, right? Well, the way I would decide this parameter, the prior on this parameter, would be by just visualizing it on the millisecond scale, having defined a prior on the log scale, and then trying to understand what it implies, whether it reflects the reality for me or not. Because I've been doing research on reading, for example, for decades, and so I have a pretty good idea what a plausible range of button pressing times is going to be, right? So I use that knowledge to decide what prior to use, but you could use a more uninformative prior here and see what happens. It's a good exercise to try that, okay? And similarly for sigma, I'm going to define a standard normal prior, mean 0 standard deviation 1, right? And the third prior, this is the most interesting one, right? Usually this is the parameter that allows us to do our scientific inference for the research question we are trying to answer, the beta parameter, right? So for that parameter, we can start by defining a very uninformative prior, a standard normal 0, 1 prior. This is very uninformative. It doesn't look like it's going to cause a lot of variability, but it is, because it's on the log millisecond scale, right? Once I transform it back to the millisecond scale, this prior will imply a lot of variability in the effect of the predictor on, that is the trial ID, on button pressing time. So we can investigate this now. It's very easy to investigate this. How do I do that? I do that by doing prior predictive checks, okay? So the way we do this, earlier I had shown you how to do prior predictive checks by writing your own function and defining priors on the parameters and then just generating data using those priors, right? But now I'm going to show you a more convenient method for doing this using the BRM package, BRM function. What this function does, this function specifies the model that we want to fit, right? This is just like the standard linear model, reaction time as a function of intercept and slope, right? The center trial as a predictor. And we are going to define, this is the new thing here. The family is a log normal, not a Gaussian anymore. And then, of course, as before, I have prior specifications for the intercept, the sigma, and the slope parameters. Okay, so these are the priors I just showed you. What is new now is that I've got this new specification here which says sample prior only. What this does is it ignores any data that go into this data specification here. So what I have put in here, this data df spacebar ref, is actually I've just created a new data frame, just a reference data frame that doesn't contain any reading times. It just has basically the IDs, you know. I'm never going to use those reading times for generating the prior predictive distribution. Why is that? That's because the prior predictive distribution by definition does not rely on any data. It's based on the model plus the priors on the parameters. So I'm only going to use that, but for technical reasons, BRM requires a data specification. So we're going to put in a dummy data set, you know, which doesn't actually do anything in this modeling here. So what this piece of code will produce is that it will produce the prior predictive distributions. This sample prior only command ensures that I produce the prior predictive distributions to understand what the implications are of the prior specifications that I have, right? So this is a very important thing that I'm showing you. What we do is whenever we are doing some modeling, we come up with some priors. You might feel unsure about whether your priors make any sense or not, right? But you can always check this by producing prior predictive data to see if the data that you produce before seeing your experimental data, right? The data that you produce, do they make sense or not? That's the step that we are doing to decide on whether our priors are reasonable or not, okay? All right. So one other thing you can do to understand whether your prior predictive distributions are reasonable or not is, instead of looking at the prior predictive distribution per se, what you can do is you can look at some statistic from the prior predictive distributions that tells you what the range of variability of that statistic is. For example, I could look at the median difference between the center point of the trial, so the value 0 and 0 plus 1. Right, so that's what the slope tells me anyway, right? So what I'm going to do is I'm going to look at the median difference between the 0th and the 0 plus 1th trial on the millisecond scale, and so I can do that here. So let's do this. So what I have is, this is the PP check function that we've seen before. This can be either the prior predictive or the posterior predictive, depending on what you put into the data, into this function, right? So here what I've got is my fit prior press trial, right? That was this function here, fit prior press trial function object. This is my BRM object, right? And what I'm saying is I want the prior predictive check to be about the statistic of interest. And what is that statistic? Well, I defined a function here that computes the median difference between a point x and x minus 1, right? So what's the impact of going from one trial to the next here, right? Okay, so, and I've got some other specifications here. For example, the bin width that I want and the Cartesian coordinates and so on can be defined here. So what you get as a result is a prior predictive distribution of the median difference, right, between one trial and the next in your model. Right? So this is now telling you what will be the impact of going from the 0th trial, that is the center point of the experiment, to one step forward. Right? What will be the impact on your button pressing time, given the prior distribution that you have. So the goal here is to try to understand whether this would be a reasonable prediction of the model or not, a priori, before seeing any data. Right? And so what we can see is that this is quite a liberal prior that we defined. Remember that the beta parameter had a prior of standard normal 0, mean 0, standard deviation 1. That turns out to be a very liberal prior because it allows for every unit increase in trial ID, right, starting from the mean of the experiment, the average trial ID. It predicts a gigantic range of variability, like up to 20,000 milliseconds, right? That's not really plausible, right? Even though these are rare events here, these are rare predictions, it's still possible, and it seems like unusually large to me for a single, button press causing this kind of change, right? So we could think now of using a more informative prior on the log scale for the beta parameter. So the beta parameter, as I said, is where all the interesting action is for the scientific question we are trying to answer, which is there an effect of trial ID on reaction time, on reading time, or button pressing time? And so we can try out a more constrained prior. Instead of the standard normal, we tighten the prior to be centered on 0 with a standard deviation of 0.01. Right? This looks very tight, but it's actually going to turn out to be quite reasonable, as I will just show you. So what I've now done is I've refit the model, right? And this time I've used a more informative prior for the slope parameter. Everything else is the same. I haven't changed anything else. So I've just made a minimal change to this model, and then I can examine the distribution of the median differences that I showed you earlier, and now it's much more reasonable, right? So with a standard, with a standard normal, I had broad range of variability on the prior predictive median differences, right? But now I have much tighter distribution around 0, and so I would be happy enough with this as a starting point, because I know that once the data come in, the posterior for the slope will be informed by the data, right? So if there's any other properties in the data that change the prior distribution, they will be very influential because I have a lot of data in this situation. And as you do more and more Bayesian modeling, you will develop experience and understand whether you have enough data or not. And of course, you can always check with different priors whether you are influencing the posterior distribution unduly using an overly tight prior, for example. This rarely happens to me, though, that I have an overly tight prior. I generally have mildly informative priors, and only in very rare situations would I use an informative prior, and that would be a situation where I'm building on previous decades of work on a particular problem. I know a lot about my problem, and I have pretty good evidence from previous work. I would put that into the model in the form of a prior, for example, on the beta parameter, right? So this is a great example of how you can build on prior knowledge, right? If you use these prior specifications in an informative way. But in most of the cases, you can work with mildly informative priors and get very reasonable estimates from the posterior distribution, which you can, of course, check, and you should check, right? Okay, so now that we have decided that we're going to work with this prior, it's good enough, right? Given the prior predictive distribution of the median differences, we are going to now fit the model.